So they're incredibly stable. They don't just vanish when they bump into another particle.
Right. And that stability is what makes them so interesting for building quantum computers, specifically for creating something called qubits.
The building blocks of a quantum computer.
Exactly. Normal qubits are super fragile errors, but qubits made with Majorana quasiparticles, way more stable, much less prone to errors.
So potentially a much more powerful and reliable quantum computer.
Exactly. And think about it, a computer that uses these Majoranas could solve problems in seconds that would take our best supercomputers billions of years.
It's almost impossible to imagine the kind of problems we could tackle with that kind of computing power.
Oh, absolutely. Medicine, materials, science, artificial intelligence, it could completely revolutionize those fields and more.
So where do we even find these Majoranas? I know the search has been going on for ages, both in the huge world of particle physics.
Right, like at CERN smashing atoms together.
And also in the tiny world of condensed matter systems.
That's where things get really interesting.
Because we might be able to actually create them, not discover them out in the universe, but build them ourselves.
You got it. The idea is that Majoranas can emerge as these special states called zero-energy states at the edges of certain types of materials.
Edges of materials.
Yeah, think of it like, imagine a rope.
Okay.
The ends of the rope, they act like separate things, right? But they're fundamentally linked, part of the same rope.
Okay, I see where you're going with this.
Those ends of the rope, that's kind of like what Majorana quasiparticles are like. They exist at the edges of certain superconducting materials, and even though they're at opposite ends, they're intrinsically connected in this bizarre quantum way.
So even on opposite ends of a material, they're linked in some way we can't easily visualize.
Exactly, and it's that connection that could make them perfect for building those stable qubits for quantum computers.
Okay, my brain is already starting to hurt, and we haven't even gotten to how scientists are actually trying to make these things.
Oh yeah, the experiments are where it gets really wild.
So how do they go about creating systems where Majorana particles might show up?
Well, one way is by using something called the Kitaev chain. Think of it as a physicist's playground.
I love how physicists have these theoretical playgrounds.
It's brilliant. The Kitaev chain is basically a simplified model of a one-dimensional topological superconductor.
Okay, a topological superconductor. That's another one of those terms that makes my head spin.
It's basically a special type of superconductor with some very unique properties. But in the Kitaev chain model, it's simplified down to a line of atoms with very specific properties.
So they arrange these atoms in a specific way, and then...
They tweak things like how easily electrons can hop between those atoms, or how those electrons pair up because of the superconductivity. And if they get those parameters just right, they can potentially create the conditions for Majoranas to appear at the ends of that chain.
So it's almost like atomic level alchemy, right? Arrange the atoms just so, make them superconducting, and poof, Majoranas.
It's pretty wild. And they're actually doing this in labs right now.
No way. Using what, like tiny tweezers to move atoms around?
Well, they use something called a scanning tunneling microscope, or STM. It's this incredible tool that lets them not only see individual atoms.
Wait, you can see individual atoms?
You can, and not just see them, but manipulate them. So with an STM, they can actually pick up and move individual atoms.
That's insane.
Right. So what they're doing is building these chains of atoms on top of superconducting surfaces.
What kind of atoms are we talking about?
They've tried iron atoms on a rhenium surface. Rhenium's also the superconductor.
So they build these tiny chains of iron atoms, one atom at a time, on this rhenium surface.
Yeah. And as they add more iron atoms to the chain, they watch for changes in the chain's properties, looking for signs of those Majorana quasiparticles.
It's like they're playing with atomic Legos, building this exotic quantum system brick by brick.
Huh. That's a great way to put it.
I can't even imagine the level of precision needed to do that.
Oh, it's incredible. And they're not just using iron and rhenium. They're also experimenting with niobium as the superconducting surface.
Niobium. Why niobium?
Well, niobium has this larger energy gap compared to some other superconductors, which basically makes it easier to spot anything weird happening at zero energy.
Ah, so it's like niobium gives them a clearer view of the energy landscape where these Majorana signatures might pop up.
Exactly. And they've been building chains of manganese atoms on niobium instead of iron.
Manganese. Interesting. And have they seen anything promising? Any hints of Majoranas?
They have. As they added more manganese atoms to these chains, they started to see a gap forming around zero energy in something called the band structure.
Okay, hold on. Band structure. Could you explain that one for our listeners who might not be familiar with it?
Sure. It's a bit technical, but basically, the electrons in any material can only have certain amounts of energy, like they're on a staircase.
Okay, so they can't just have any energy. They're restricted to specific levels.
Right. And the band structure is basically a map of all those allowed energy steps for the electrons in that material.
So it's like a fingerprint of the material's electronic behavior.
Yes. And with these manganese chains on niobium, as they got longer, a gap started opening up in that band structure right around zero energy.
A gap at zero energy.
Exactly, and that's a big deal because that's exactly what theoretical physicists predicted would happen in a system with Majorana quasiparticles.
So they're not directly observing the Majoranas themselves, but they're seeing this gap appear in the energy levels, which is a strong hint that they might be there.
It's like trying to map the interior of a mountain just by listening to how sound echoes off its walls.
Okay, I kind of get that analogy.
That's what these scientists are doing, but at the atomic scale, they're looking for echoes in the energy landscape to try and map where these Majoranas might be hiding.
It's incredible, but how can they be absolutely sure that this gap is because of Majorana particles and not something else entirely?
That is the million-dollar question, and that's what we'll be diving into next. Stay tuned.
Okay, I'm hooked. We'll be back after a short break to talk about the experiments that are really pushing the boundaries and trying to prove once and for all that Majorana quasiparticles are real.
So how to be sure, right? It is tricky. But there are a few things scientists are looking for, like those smoking gun signs that really point to Majoranas.
Okay, lay it on me. What are the telltale signs?
Well, remember that rope analogy. Majoranas should always appear in pairs, one at each end of the chain. Like you can't have one end of a rope without the other.
So if they only see a zero energy state on one side, it's probably not a Majorana?
Right, it's got to be a double feature. And then there's that specific energy signature they should have. Because they're zero energy states, they create a unique peak at zero energy when you look at the energy spectrum.
So not just any zero energy state, but one with that distinct energy peak.
Yeah, like a beacon, right there at zero energy. And then things get really weird.
Oh, I love when things get weird. Hit me.
Those two Majoranas at either end of the chain, they should be entangled.
Ah, quantum entanglement. It's one of those things where even when you think you get it, you don't really get it.
Right, it's basically like two particles, no matter how far apart they are linked in a way that just defies classical physics.
Yeah, so you do something to one, the other one reacts instantly, even if they're light years apart.
Exactly, like they're communicating faster than light, which is impossible according to everything we know about physics. Einstein called it spooky action at a distance.
I love that he called it that. So scientists can actually test for this entanglement with Majorana particles.
Yeah, they can like poke one end of the chain and see if the other end reacts immediately. If it does, that's strong evidence for entanglement, a key characteristic of those Majoranas.
Has anyone actually done that experiment?
There was this one study. Researchers were working with those chains of manganese atoms on a niobium surface, and they found that when they added just one more manganese atom to one end,
Okay.
it caused energy changes at both ends of the chain.
Whoa. So it's like those two ends were communicating faster than light.
It's one of the most exciting findings so far. And there's another cool experiment. We've been talking about how scientists can see individual atoms with those SPMs and map out those energy levels in materials, right?
Right, and they saw that gap pop up in the band structure, which hinted that those manganese chains on niobium might be topological superconductors with Majorana particles at their ends.
Exactly. But what's really mind-blowing is that they figured out a way to actually map the energy structure where those Majораnas live with incredible precision.
Wait, hold on. You're saying they can visualize the energy landscape where these quantum particles exist? How do you even see something that's inherently quantum?
It's wild, right? They do it with something called quasiparticle interference mapping. It uses the fact that in those finite chains, the electron waves are bouncing back and forth.
Like ripples in a pond.
Yeah, and those ripples, those interference patterns, actually reveal information about the energy landscape.
So they're like listening to the echoes to map out the terrain.
Kind of. But at the atomic scale, by carefully measuring those interference patterns at different energies, they can piece together a map of the allowed energies for the electrons.
So like creating a topographic map, but of the quantum world.
Exactly. And they did this experiment. They mapped the band structure of a manganese chain on niobium, and it showed clear signs of a topological superconducting state.
And that's a strong indicator of those Majorana zero modes.
It's huge evidence. But there's a twist. They didn't see those Majorana modes exactly where the simpler models predicted, right at the ends of the chain.
Oh, what happened?
They found these weird side features where the Majorana modes seem to be shifted a little bit away from the chain's ends.
Side features? That sounds unexpected.
It was, and it highlights how those simple models we've been talking about don't always capture the full complexity of what's really going on.
So real life is messier than the theoretical models.
Always. We've been thinking about these chains in isolation as if they're perfectly one-dimensional, just a straight line of atoms.
Right, nothing else around.
But in reality, they're sitting on a three-dimensional superconducting surface, and that can have some influence.
So the interaction with the surrounding material is more complex?
Exactly. Plus, we've been assuming that these chains only have one type of orbital for the electrons.
Orbitals. Now we're getting into the weeds of atomic physics.
Aha, I know. But it matters because atoms have multiple orbitals, each with different energy levels.
So the models with just one type of orbital might be too simplified.
Right. And when you factor in those multiple orbitals and the influence of the substrate, those theoretical predictions change.
So those side features where they saw the Majorana signatures, that means the Majoranas are still there, they're just not exactly where we thought they'd be.
That's what the latest research suggests. The theory says that if they could build much longer chains, those Majoranas would become more localized at the ends, as those simpler models predict.
So it's all about scale, longer chains, more isolating Majoranas.
Seems like it. But building those ultra-long chains, that's a whole other experimental challenge.
I can imagine, but let's say they can create these Majoranas, get them where they want them. How do you control them? If we want to build quantum computers, we need to be able to manipulate these things.
You're right, that's the next big hurdle, and that's where braiding comes in.
Braiding? Wait, like with hair. Am I missing something here?
Not quite like hair, but the idea is kind of similar. Imagine those Majorana particles like beads on separate strings. Braiding involves carefully swapping their positions, and it's this exchange that's key for doing quantum calculations.
You're saying the act of braiding these particles is a form of computation.
Exactly. It has to do with the topological nature of these systems. When we exchange the positions of those Majoranas, we're changing the topological structure of the system, and that affects the quantum information stored in those particles.
Okay, I'm following, but how do you actually braid particles that are invisible and in the quantum realm?
It's a huge challenge, but one approach involves those networks of atomic chains, remember?
Like building tiny mazes for them.
Yeah. T-junctions, Y-junctions, all sorts of intricate patterns built with atoms. The idea is to move the Majoranas along these paths, effectively braiding them.
And how do they control that movement?
Well, one way is to use magnetic fields, carefully calibrated, to kind of nudge those Majoranas along.
So they're like sheepdogs, herding those quantum particles around with magnetism.
Ha! I like that. And there's another crazy idea of measurement-based braiding.
Measurement-based, how do you braid something just by looking at it?
I know, right? It's super counterintuitive, but it comes from that link between measurement and entanglement in quantum mechanics. When you measure a quantum system, you mess with its state, right? And if it's entangled with another system, your measurement affects both of them instantly.
Spooky action again?
Exactly. So the idea with measurement-based braiding is that by carefully making a series of measurements on those entangled Majoranas, you can essentially braid them without actually physically moving them.
Whoa. So we've gone from hunting for these elusive particles in the universe to creating them atom by atom, and now we're talking about braiding them to build quantum computers.
It's incredible, right?
It really is. So after all this, what's the one thing you want our listeners to remember about these Majorana particles?
I want them to remember this. Majorana particles aren't just theoretical, they're real.
Yeah, and we're actually creating and controlling them right now in labs.
We're on the edge of a whole new era in technology, and these particles could be the key.
It's kind of hard to wrap your head around. So we've talked about braiding these Majoranas as the way to control them, but how do you actually do that?
Well, one promising approach uses those networks of atomic chains we were talking about, building those miniature circuits, remember?
Right, those tiny mazes for the Majoranas to move through. But how do you actually get them to move along those paths?
The million-dollar question. One idea is to use super precise magnetic fields to sort of guide them.
Like those magnetic sheepdogs, right?
Exactly. But there's another really cool concept using something called electron spin resonance, ESR.
Oh, I've heard of that. That's a way to play with the spin of electrons.
Right, yeah, it is. And remember, those atomic chains need specific magnetic properties for the Majoranas to show up at all.
Right, like those iron chains on rhenium or manganese on niobium. The magnetism matters.
Exactly. So with ESR, you can target specific atoms in the chain and flip their spin.
Flip their spin? How do you even...
It's amazing what they can do now. And when you flip the spin of one atom, it changes the magnetic environment right around it.
Ah, I see. So by flipping spins, you can kind of nudge those Majorana particles along those paths in the maze.
You got it. And while it's still early days, those theoretical simulations suggest it could actually work. Oh, and there's one more idea I didn't tell you about yet.
Okay, now you've got me really curious.
It's called measurement-based braiding.
Measurement-based? Hold on. How can you braid something just by looking at it?
I know, it sounds nuts, right? But it has to do with that weird connection between measurement and entanglement. You measure a quantum system, you inevitably change it, right?
Right, like the act of observing influences it.
Exactly. And if that system is entangled with another one, your measurement affects both of them, no matter how far apart they are.
Spooky action.
Right. So the idea with measurement-based braiding is that you carefully do a series of measurements on those entangled Majoranas, and that can essentially braid them without even touching them.
Whoa, that is even weirder than actually moving them around. It's almost like magic.
It's pretty incredible. And it could be a much more efficient and reliable way to do those quantum computations with Majoranas.
So it's like we've gone from searching for these things out in the universe to building them atom by atom in the lab to now potentially braiding them to make quantum computers. It's just mind-blowing.
It really is, and we're just at the beginning. There's so much more to learn about these particles and the crazy technologies they might lead to.
All right, well, after this incredible deep dive into the world of Majorana quasiparticles, what's the one thing you really want our listeners to take away?
I think the biggest thing is to remember this. Majorana particles are not just theoretical.
They're real.
They are. And scientists are actively making and controlling them right now. We are on the cusp of some incredible breakthroughs.
It's an exciting time to be alive, and it sounds like the story of Majorana particles is just getting started. Thank you so much for joining us on this deep dive.
It's been my pleasure, and I can't wait to see what happens next.
To all our listeners, stay curious, and we'll catch you next time for another deep dive.